Hi everyone, my name is Farhan and this is my final project report. I'll be covering this paper which is called Optimizing over an Ensemble of Neural Networks. It came of University of Connecticut and University of Cincinnati. Here's the outline of my presentation. I'll quickly go over the introduction and motivation for this work, summarize the paper, and then critically review every section of the paper, and followed by some proposed extensions and future work. So introduction and motivation. So the idea here is to embed neural networks within optimization problems. Neural networks are very effective in capturing nonlinear relationships within the data. So if we can train a neural network and then fix its weights and biases as parameters, and then model it as an MILP problem, we can check if the neurons that were turned on or off were the best neurons to be turned on or turned off. So what we do is we model the ReLU function, linearize it, and model it inside an MILP problem, and see if we can enhance the decision making. So neural networks are not trained optimally. We can use this approach to figure out which of the neurons to turn on or turn off. However, the issue here is that a single neural network is sensitive to noisy data. Outliers affect its performance a lot. And it's also likely to overfit, where it memorizes instead of learning. And it often converges to local minimas as well. What do we do to overcome these issues? We consider an ensemble of neural networks, where instead of using one, we use three or more than three neural networks. The advantage of this approach is that the overall accuracy can be improved by combining the predictions of different models. It's typically averaged. This also prevents it from overfitting, since there are multiple models trying to predict the same thing, and you're combining their outputs. The model is less likely to overfit to the data, and it's more robust to noisy data. It doesn't get thrown off by outliers, and it's less likely to get stuck in a local minimum. However, going from a single neural network to an ensemble neural network leads to computational load, increased load. So for one neural network, let's say there are 2,000 neurons and we need 2,000 binary variables for it. But for better performance, we consider 5 neural networks. Then we will have 10,000 binary variables. So it's very hard to solve MILP with so many problems, and that is the major problem with the whole idea here. But let's see what the paper does, how the paper handles it, and what is their approach. Okay, so they model it as an MILP problem, solve it using branch and cut algorithm. They linearize the ReLU function using standard practices, and then where they need a lower bound and upper bound that needs to be determined for every binary variable. Sorry, every neuron. Every neuron has its specific lower bound and upper bound, which leads to considerable pre-processing. Then they use a two approach method. Their objective is to maximize the average output of an ensemble of neural networks. They model it by linearizing ReLU, embedding the input and output layer constraints, and combining the train weights and biases as the output of each neuron. Methodology, as I said, significant pre-processing to compute the lower bound and upper bound for every neuron. In the first phase of solution, they solve it with valid inequalities within a certain time. If it is not solved within that time, they move to phase 2. In phase 2, they use Lagrange multipliers to solve the problem within a set time. And the testing, they do it on 4 benchmark problems and 2 sampling methods, and then 2 real-world data sets. And then compare single versus ensemble neural networks, as well as branch and cut versus the proposed methodology, phase 1 and phase 2. So that is the overview of the paper. Now we'll go inside and critically review every section of it. So the first thing to look at is the literature review. Previous works, the older works on this topic considered hyperbolic tangent activation functions and constraint programming. More recent works focus on ReLU activation and branching cut optimization. And a lot of research is dedicated to reducing the solving time when you're using branch and cut. The problem here being a large number of binary variables making it hard to solve. So the current study builds upon this, and they are the first study to use an ensemble of neural networks instead of a single neural network. They stay in tune with present trends, which is to focus on ReLU and several approaches like regression relaxation to speed up the process. And one of the other things in present trend is to optimize other types of neural networks, for example, graph neural networks. So critical reviews of the literature review looks like it was done well in this paper. We next come to the review of the mathematical formulation used in the paper. Let's look at the assumptions first. The first assumption is that they only consider ReLU activation function for all hidden neurons, which I believe is okay since most neural networks use ReLU for hidden neurons. Another assumption is that there's only one output with ReLU activation. This can be very restrictive as for classification problems, the activation tends to be sigmoid or softmax. Additionally, a single output neuron isn't very practical. The objective of their optimization problem is to maximize the output only. They don't consider minimization of output or loss, making the approach a little specific. This may not be a big problem. Then when they're linearizing ReLU function using lower bounds and upper bounds, I noticed that these bounds are very problem dependent, neuron dependent. So this requires substantial pre-processing, and I would hope for a different approach in the future that does not rely on such extensive pre-processing. However, the biggest challenge that remains is the large number of binary variables. How to handle that? Now let's look at the solution methodology. First step being pre-processing lower bounds and upper bounds. The authors compare and contrast the two methods, interval arithmetic and solving two MILPs, both present in the literature. So interval arithmetic provides very loose bounds, whereas solving two MILP is very time consuming. So they provide a trade-off approach where they identify critical neurons and do the MILP approach for only those neurons. They do this by checking the difference between expected output and actual output of the neuron. So the critique here is, while this reduces the processing load, it can lead to several neurons having loose bounds. Then they phase one of the methodology. Now this requires, they use valid inequalities over here to speed up the solution process. They use dual variables from the integer relaxed version of the problem to generate inequalities that provide an upper bound to the maximization problem. In phase two, they use Lagrangian relaxation, where they relax the set of constraints corresponding to the first layer of neural network being equal to the input. I'm not sure entirely why they choose to use this constraint to relax. I thought there are other constraints that can be relaxed as well, but this is what they chose. So this constraint becomes a penalty term adds to the objective function as with a penalty term equal to the Lagrangian multipliers. So they claim that it will be easier to solve now, and the final method is called enhanced NN. The overall critique of the methodology is that authors use multiple techniques to reduce solving time, instead of finding a technique that works best, that is probably most suitable to the problem. So it's not like using an intelligent approach, it's like throwing the kitchen sink at it. Through every method to reduce solving time, one of them would work. So I felt that the methodology was not very intelligent. Okay, now the review of the data. They use 4 standard functions, which are populated using 2 sampling methods, Latin hypercube sampling and symmetric positive definite matrices. So this itself gives them 8 cases, which they enhance further with the help of many hyperparameter tuning, and get a total of 1280 test runs. So my critique here is that these are very simple test functions. So perhaps two were sufficient. We probably did not need 4 test functions here. And instead of experimenting with 2 sampling methods, they could have chosen the one that is more suitable, instead of showing us results with every possible combination. I feel like 2 test cases were sufficient for these examples. We did not need that many test runs. Because at the end of the day, 1280 test runs with most of the data being similar to each other, it just becomes like a lot of results on similar data sets that does not add a lot of value. It felt, at this point, the paper felt less like a research paper, more like a project report, where the grad student is trying everything he learned in the class and writing in his homework paper. This part was not very satisfying to go through. Then they moved to show the practicality of their approach using what they call 2 real-world data sets. Wine and concrete, these are fairly simple data sets, not large enough for neural networks. The wine dataset has only 11 features and concrete dataset has only 8 features with 1500 and 1000 samples. It's such a small dataset that traditional machine learning methods can work great on this. You can use linear regression and get great results on it. You don't even need neural networks here. So what they claim to be real world datasets were not real world or not hard enough, not suitable for deep learning at all. Their largest test instance has 5 ensembles with 4 layers and 40 neurons in each layers, totaling to just 800 neurons. And we know from practice that typical deep neural network for any practical problem has 2000 to 5000 neurons at least. So 800 neurons is far from practical. So it is not hard enough test case to really test their theory. It's fairly simple. So the methodology seemed okay, but the data sets and the testing they have done seems pretty average to me. So a quick review of the results. The paper contains several tests, of course. First, they compared the solution quality between a single neural network and an ensemble. As expected, ensemble is more stable and gives a better overall performance. Then in the second set of testing, they compared the baseline as just branch and cut with their approach, which uses the valid inequalities and Lagrangian relaxation. So their approach reduces solving time and gives lower MIP gap. Uh, Although most testing is redundant or not practical, here are some pros and cons. They use something called Mahalanobis distance, which is the difference between optimal point and other data points. I thought that is a good metric to use and measure the performance of a model. The implementation details are provided really well. If one has to reproduce it, it will be easier to do that. Resolution of results is also good. However, and the negative, several hyperparameters are left on default settings, and the neural network used for the comparison are not very deep. So the proposed approach may not work very well when we are considering practical neural networks. So this was the critical review of the paper. I have a couple of small extensions that I have suggested. First is a modeling improvement. I understand that it's hard to get rid of lower bound and upper bound right now. So what can we do to have a single lower bound, a single upper bound for the whole model? So what we can do is, if the application is not very sensitive to normalization, where normalization makes you lose details of the features, where you can use normalization when it's a viable option, you can normalize input and output, you can normalize weights and biases. In that case, the output is likely to be between -1 and 1. So we can set lower bound to -1 and upper bound to 1. However, this obviously needs a lot of testing and evaluation to see if it really works. But this is some initial ideas I had. Second, for the methodological improvement, how do we handle large number of binary variables? There should be an intelligent way of doing this, because we have thousands of binary variables and it's not easy to solve the problem. For these kind of problems, Lagrangian relaxation is pretty good, but it requires you to solve every subproblem, which is a problem in itself. It's very computationally expensive. There is another approach in literature that's called surrogate Lagrangian relaxation. The advantage here being that you don't need to solve all subproblems optimally. You only need to solve a subset of subproblems and get a near optimal solution. So this could greatly reduce the computational burden. But again, these extensions need to be tested extensively to check how effective they are. Considering the limited time, I couldn't implement the extensions, but if I was to extend this paper, I would first try to reduce the requirement, the pre-processing required to get low bound and upper bound. If not for the entire network, I would at least try to get a low bound and upper bound for the layer, one particular layer of the neural network. And of course, a more intelligent way to overcome the challenge of having a large number of binary variables. So in conclusion, the paper reviewed in this project optimizes over an ensemble of neural networks. They only use a ReLU activation and only one output neuron. The one output neuron is a major restriction, other things are fine. They need low bound and upper bound and a binary variable to capture the ReLU action. These bounds, calculating these bounds is a very time intensive procedure. They use valid inequalities and Lagrange relaxation to speed up the process, but it's not a very intelligent approach to just try different things. Instead, the author should have found the most suitable approach. Testing was the weakest part of this paper. The data sets used, the testing done. The rest of the paper I thought was okay, but testing was really subpar. Most of the results were either redundant or not practical at all for deep learning. Extensions suggest an approach we can take towards improving the modeling and methodology. These are my references, and thank you very much for listening.